Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Confinement of a particle in a box and in 3D, that is quantum dot, from the paper Physics at Nanoscale. So students, let us see what we are going to learn in this module. First, particle in one-dimensional box, finite and infinite. Second, particle in 2D box, that is a rectangular infinite box. Third, particle in a 2D circular box. Fourth, we will be discussing particle in a 3D cubical infinite box and 3D spherical box. So students, let us start with a basic introduction about the module. The properties of materials, they are strongly influenced by the size of the particle. For example, carbon is a non-metal, but when considered at the nanoscale single layer, allotrope of carbon, that is graphene, is one of the best conductors. The phenomenon that can be used to explain the size dependent characteristics of materials is quantum confinement. So, quantum confinement effects, they are generally observed when the size of the particle is smaller comparable to the de Broglie wavelength of an electron. So the effect which describes the phenomenon resulting due to the squeezing of particles, which may be electrons and holes, into a dimension that approaches a classical limit, so that various quantum effects are manifested. So in this regime, the energy of the particle is no longer continuous, but it is discrete. Quantum confinement effects, they are observed in low dimension, 2, 1 or 0 dimension. So when a particle is confined in 2 dimension or in a plane, then particle's motion is quantized along the direction of the confinement, say z-axis, and the particle's motion is classical, that is, it is free to move in the xy plane. So the system in 2D is also known as a quantum well. So in the case of one dimension, the particle's motion is quantized due to confinement in 2D, say in xy plane, and classical in one dimension along a certain axis, let's say z-axis. So the system in 1D is also known as a quantum wire. In the case of one dimension or the 0 dimension, the particle's motion is quantized in all the 3 dimensions due to confinement along x, y and z directions, and this is known as a quantum dot. So in these systems, the spatial dimensions, they are of the order of de Broglie wavelength of the carriers, and therefore the carrier energy states, they become quantized. So as a result, the electronic, electrical and optical behavior of the carriers are governed by quantum mechanics along 1 dimensions, 2 dimensions and all the 3 dimensions in a quantum well 2D, quantum wire 1D and quantum dot 0D respectively. Quantum confinement in nanostructures. An overview of it. Electrons confined in one direction, that is a quantum well, thin films, where the electrons can move in 2 dimensions. This is evident from this figure. Then the movement of the directions are given by kx and ky. Next, the electrons confined in 2 directions. These are quantum wires, where electrons can easily move in 1 dimension, that is along kx only. Next is electrons which are confined in 3 directions, that is a quantum dot, where electrons can easily move in 0 dimension, as it is shown in this figure. So, each further confinement direction changes a continuous k component to a discrete component characterized by a quantum number n. Now, if we start discussing about the density of states, DOS, density of states, equal to dn by dE, which is equal to dn by dk multiplied by dk by dE. So here n as a function of k is equal to k space volume divided by volume per state, which is equal to 4 by 3 pi k cube. Now if, as shown on the right hand side figure, which shows the density of states for charge carriers in the structures with different dimensionalities. Now here we have taken a sphere. So the k space volume is given by 4 by 3 pi k cube divided by 2 pi cube divided by v. Now this table tabulates the structure, the degree of confinement and the dn by dE for each structure. Now if we have a bulk material, then there is 0D degree of confinement and dn by dE is root E. For quantum well it is 1D and dn by dE is 1 by root E. Quantum wire it is 2D and dn by dE is 1. For a quantum dot we have 3D and dn by dE is given by delta E. Particle in a 1D infinite potential well. So an infinite potential well has zero potential inside and infinite outside, and it is described by Vx is equal to infinity for x less than 0 and it is 0 when x is varying between 0 to a, and it is infinity if x is greater than equal to a. The solution is given by psi x is equal to a multiplied by a exponential iota kx plus b exponential minus iota kx. Now after applying the boundary conditions and rearranging the terms, energy is given by n square h square by 8 ma square. And by normalizing the wave function such that the probability of finding the electron over all the space, we get psi x is equal to root of 2 by a multiplied by sine kx. So the energy of an electron inside an infinite well can only be at some finite and discrete levels as opposed to that of a free electron. Potentials and quantization. Now students, previously we have calculated the wave function and the energy for a particle in one dimension infinite potential. So as we know that the energy is quantized, so this figure A shows the different particle energies for different values of n, that is E is equal to n square h square by 8 ma square, where n varies from 1, 2, 3, so on, and the wave function is given by psi x is equal to root of 2 by a multiplied by sine of n pi x by a, where n is equal to 1, 2, 3 and so on. So the figure B indicates the particle wave function psi, that is for n equal to 1 we have psi 1, n equal to 2 we have psi 2 and n equal to 3 we have psi 3. And the last figure represents the probability density, that is psi star psi for n equal to 1, 2, 3 and so on, that is psi 1 square, psi 2 square and psi 3 square. So we can conclude that for the probability density becomes positive for all the values of n. Particle in a one-dimensional finite box. So students, from quantum mechanics, we know that as the potential is zero inside a box, the solutions in the box region will be wave-like, and in the barrier region, the solution will be exponentially decaying. So the potential V is given by Vx is equal to V if x is less than equal to 0. So students, you can see in this figure, this is shown by region 1. Now Vx is equal to 0 if x varies from 0 to a. This is depicted by region 2. Now region 3 is Vx is equal to V if x is greater than equal to a. So the solutions in the 3 region indicated are psi 1x is equal to a multiplied by exponential beta x plus b exponential minus beta x, psi 2x is equal to c exponential iota kx plus d exponential minus iota kx, and psi 3 is equal to f exponential beta x plus d exponential minus beta x, where beta is equal to root of 2m bracket v minus e by h cut square and k is equal to root of 2me by h cut square. So now by applying the boundary conditions b is equal to 0 and f is equal to 0, due to the finiteness of the wave function outside the box, we get psi1x is equal to a exponential minus beta x, psi2x is equal to c exponential minus kx plus d exponential minus kx, and psi3x is equal to d exponential minus beta x. So now if we apply the boundary conditions at the interface and rearranging the energy of an electron inside a finite well can only be at some finite and discrete levels, which are obtained by solving the transcendental equation, that is tan of root of 2me by h cut square the whole multiplied by a bracket close equal to 2 multiplied by root of e bracket v minus e bracket close divided by 2e minus v. So students, let us consider an example for an electron in a potential well, that is the hydrogen atom, consisting of a proton and an electron which is revolving around the nucleus containing one proton. And as you can see over here that the potential the electron is experiencing is given by minus e square by r, that is with increase in r the potential is increasing on the negative side. So now solving the Schrodinger equation, we get that the energy is quantized and all the energy levels corresponding to the various values of n, that is if we go from n equal to 1 to 2 till infinity, the energy is increasing, that is it is going from the negative to the positive side, and the maximum energy which we can achieve is 0. So here V is not a constant but a function of R. So the effect of constraining potential is that the energy of the hydrogen atom becomes quantized. Particle in a 2D rectangular box. So the potential of a 2D rectangular box is described by Vxy is equal to infinity if x is less than 0 and y is less than 0. So students, as you can see in this figure, it is on the left hand side of the origin. Now the potential is 0 if x varies between 0 and a and y varies between 0 and b. And it is again infinity if x is greater than equal to a and y is also greater than equal to a. So here a is on the x-axis and b is on the y-axis. So now if we write the Schrodinger equation, that is minus h cut square by 2m multiplied by bracket d square by dx square plus d square by dy square plus vxy bracket close psi xy equal to e psi xy. Now if we'll consider the solution of above equation is psi xy equal to psi x multiplied by psi y, where psi x and psi y are the functions of x and y only. So now if we'll substitute this solution in the Schrodinger equation where v is equal to 0 and writing the equations using variable separable method, then we get two equations, each consisting of one variable only, that is either psi or psi y. So d square psi x by dx square plus kx square psi x is equal to 0. And another equation is d square psi y by dy square plus ky square psi y is equal to 0, where kx square is equal to 2mex by h cut square and ky square equal to 2mey by h cut square. So the general equation for the, or we can say the general solution for the above equation, considering the x and y solutions are independent, then we can write psi x is equal to a multiplied by exponential iota kx x plus b multiplied by exponential minus iota kx x, and psi y is equal to c multiplied by exponential iota ky y plus d exponential minus iota ky y. Now imposing the boundary conditions, that is the conditions on psi x and psi y at the boundary, we can solve after rearranging for the energy for Ex and Ey, that is Ex is equal to nx square h square by 8ma square and Ey is equal to ny square h square by 8mb square. So the total energy is given by E is equal to nx square h square by 8ma square plus ny square h square by 8mb square. And by normalizing the wave function, we get psi xy is equal to root of 2 by a sine of nx pi by a multiplied by x multiplied by root of 2 by b sine of ny pi y by b. Particle in a 2D circular box. So students, now consider a circular box of radius capital R. So the potential inside the box is 0 and outside the box it is infinity, such that the boundary conditions for the wave function would be psi r theta is equal to 0 for all the angles of theta. Now, transforming the Schrödinger equation from Cartesian coordinates to the polar coordinates, the transformation equations are x is equal to r cos theta and y is equal to r sin theta, such that r is equal to root of x square plus y square and theta is equal to tan inverse of y by x. So the Schrödinger equation for a circular box in polar coordinates becomes minus h cut square by 2m multiplied by bracket del square by del r square plus 1 by r del by del r plus 1 by r square del square by del theta square plus 0 bracket close psi r theta. It is equal to E psi r theta. Now considering the solution for the above equation as psi is equal to r ml as a function of small r multiplied by exponential plus minus mi theta. So now the radial equation reduces to a form of the Bessel's equation. This Bessel function expansion remains an infinite series which never truncates. So the quantization occurs only with the boundary conditions, that is, at the perimeter of a circular ring. So, assuming a zero at small r equal to capital R to be rho naught, then we get the ground state energy as E naught is equal to h cut square by 2m multiplied by rho naught by r the whole square, where rho naught is equal to r, the capital R, by k, which is equal to r divided by root of 1 by epsilon. So, where epsilon is equal to 2me by h cut square. So from this equation we get this expression for the ground state energy, and now putting the value of rho naught, that is, it is equal to 2.4048, which is the first root of Bessel function. Then E naught is equal to h cut square by 2m multiplied by 2.4048 by r the whole square. Now students, let us consider a particle in a 3D box. So first, here we will be discussing about the particle in an infinite cubical box. So let us consider a general case, that is a box with the dimensions A, B and C, and the potential is given by. So now students, here the potential will be a function of x, y and z, and it is equal to infinity if x is less than 0, y is less than 0 and z is also less than 0, and it is equal to 0 if x varies from 0 to a, y varies from 0 to b and z ranges from 0 to c. And it is again infinity if x is greater than equal to a, y greater than equal to b and z is greater than equal to c. So now if we'll try to write down the Schrodinger equation, then minus h cut square by 2m bracket d square by dx square plus d square by dy square plus d square by dz square plus vxyz bracket close psi as a function of xyz is equal to e psi xyz. So let us consider a solution of the above equation is psi xyz is equal to psi x, psi y, psi z, where psi x, psi y and psi z are the functions of only x, y and z respectively. So now substituting this solution in the Schrodinger equation and rearranging the terms to yield in the box region where v is equal to 0, then we get the equation only for psi x, psi y and psi z, and using the variable separable method we can transform this equation into 3 equations, each consisting of one variable only. So d square psi x by dx square plus kx square psi x equal to 0, d square psi y by dy square plus ky square psi y equal to 0. Next equation is d square psi z by dz square plus kz square psi z equal to 0, where kx square equal to 2mex by h cut square, ky square equal to 2mey by h cut square, and kz square equal to 2mez by h cut square. So the general equation or the solution for the above equation is psi x is equal to a exponential iota kxx plus b exponential iota minus iota kxx, and psi y is given by c exponential iota kyy plus d exponential minus iota kyy, and lastly psi z will be equal to m exponential iota kzz plus n exponential minus iota kzz. So now after applying the boundary conditions and rearranging, the total energy is given by E is equal to nx square h square by 8ma square plus ny square h square by 8mb square plus nz square h square by 8mc square. And by normalizing the wave function, we get psi x y z is equal to root of 2 by a sine of nx pi x by a multiplied by root of 2 by b sine of ny pi y by b multiplied by root of 2 by c sine of nz pi z by c. Now students, let us discuss particle in a 3D spherical box. So when we write down the Schrödinger equation for a circular box in spherical polar coordinates, then it is given by minus h cut square by 2m bracket 1 by r square del by del r of r square del by del r plus 1 by r square sine theta del by del theta of sine theta del by del theta plus 1 by r square sine square theta del square by del phi square plus 0 bracket close multiplied by psi as a function of r theta phi equal to E multiplied by psi r theta phi. So considering the solution for this equation, we have psi is equal to capital R as a function of r only and y as a function of theta and phi. Now substituting this solution into the Schrödinger equation and separating the variables, we can reduce the angular equation to a form of Legender's equation and the radial part to a form of Bessel's equation, and ultimately we get ENL equal to ZNL the whole square multiplied by h square by 2mr square multiplied by kr. This is equal to ZNL. So now we can summarize the quantum confinement as shown in this figure. That is, if we are increasing the diameter, that is in the nanometer range, the number of atoms are increasing from 10 to 10 to the power 9, and the spectroscopic regions, that is from molecule and then to quantum dot and then to a polariton. So Corresponding to the quantum dot, we have bulk exciton diameter. For the polariton, we have a shape resonance, and from 10 to the power 7 to 10 to the power 9 atoms having polariton as the spectroscopic region, we have the optical size resonance only when d is equal to lambda by 2. Now we have kinetic regions also, that is from 10 to 10 to the power 3 having unimolecular EH kinetics, and then above that we have many body kinetics leading to the band bending. So students, let us summarize what we have learnt in this module. First, the particle energies, wave functions and probability densities for a particle in one-dimensional infinite box were studied. Second, solution for a particle in 1D finite box is obtained. Third, the wave function for a particle in a 2D rectangular box is derived. Fourth, the solution for a particle in a circular box is obtained. Lastly, the particle in a infinite cubical and spherical 3D box is investigated, and the corresponding eigenvalues and eigenfunctions were obtained. Thank you.